Okay. So we were discussing these linear discriminant models in which we had discussed three different methods to to estimate the parameters. The that is linear discriminant analysis, Fisher's algorithm, perceptron, and least square. Right. So we were about to end at perceptron. So in just first few minutes of this class, I want to discuss perceptron, and then we'll go to the probabilistic generative models. Right. So this is just a quick recap what we have done in a previous class. This is perceptron algorithm. You are quite aware what is the equation of hyperplane. So this is the equation of a hyperplane, and I am interested in estimating my W. Here W is nothing but it is just a augmented vector where my W0 is also there inside, right? So this is what we have done. Because it is not a probabilistic model, so we have just uh, the coding for target variable is +1 and -1, right? So the target variables are +1 for if it is above the hyperplane, and -1 if it is below the hyperplane, right? We said that there is a cost function. It could be piecewise constant, but if it is piecewise constant, we cannot apply gradient descent. So we should come up with some better cost functions where we can apply gradient descents, right? So then we said that determining, then we said that this will always hold if you able to find out a hyperplane which able to classify with 100% accuracy. This we have discussed, and you have answered it well why it is so. Then we said that okay, if it is piecewise constant, we cannot apply on gradient descent. So we should not get a function where we can apply a gradient descent. So we had come up with a notion where we now are having a cost function which is piecewise, which is piecewise linear, right? So it is piecewise linear. So this is piecewise linear means, right? So here from here to here, this is this linear. From here to here, this is second linear. From here to here, this is third linear, right? So it is piecewise linear. So every time, because it is a linear, so you can always apply a gradient descent. So if you start from here, you jump from here, and finally you jump here and you converge to this point. And we have discussed like how it is piecewise linear, because now you are just taking only those points which are misclassified, and because it is misclassified, this quantity is always negative, right? So you just sum up all those negative numbers and multiply it with the negative, you will get a positive number. So it is, you are just calibrating your error, and this is how your error function look like for different value of a parameter. You apply gradient descent and you will get a unique minimum. We've said that you can apply stochastic gradient descent, and we have discussed what is okay. So we were here. In stochastic gradient descent, you just calculate the gradient. So if you come up here, this is your cost function, right? So can anybody quickly answer me if this is a cost function? I need to find out what is my what I want to estimate here. What is my variable? What is my variable? W. Yes, very good. So W is my variable. If I take a derivative with respect to W, I will get only phi t, right? Phi t. So n is just a n is nothing but it's an sample. So if you take a derivative with respect to W, you get a negative phi t, right? Negative phi t. So here this is a derivative. You put a derivative, you place a phi negative phi t, which is a derivative with respect to W. This negative and this negative will be positive, right? And this phi t, as it is coming, it comes here, right? It comes here. And this is like what is the steps you have taken, right? I told you like this will tell you the direction. and eta will tell you how long steps you have taken. So we have discussed in last class, so I don't need to discuss it again. So this is what we have, right? Then I was saying, okay, so this is my, I am somewhere here, right? I am somewhere here. This is my cost function, let's see. So I am somewhere here. So somewhere here means this is my old W, right? This is my old W. I calculate a gradient. When I calculate a gradient and take a negative direction of that gradient, so this is the negative direction, right? So this is the negative direction of a gradient, because gradient give me the positive direction where my height will be maximum. So this is that direction. I take a negative, I will get this direction. Once I get a direction, I need to choose what step size should I take. So that will be decided by eta. So eta, if I take eta very large, so I can overshoot my minimum and can land somewhere here. If I take eta very small, I can just jump here somewhere, right? So eta is like is a deciding factor how where I can go, right? So what it says now, this is one thing. The other thing is, if you have a hyperplane, let's say that hyperplane equation is x1 plus x2 minus 3 equals to 0, right? Equals to 0. So if I multiply this hyperplane with any number, right, it will, if at first it was classifying all samples correctly, and if I multiply it with some variable, let's say I multiply some constant c, will it change the classification error? Can anybody tell me this answer? Will it change the classification error? So I had first some hyperplane. It was classifying perfectly. So for example, if I draw this hyperplane, it is nothing but it is a line somewhere like this, which is nothing, x plus 1 plus x2 equals to 3. Now if I multiply this line with constant c, will my accuracy change?
Yes.
It will change.
Yes, sir. It will change.
For an example, at first my hyperplane was this x1 plus x2 equals to 3. So I had this two samples above the hyperplane, two samples below the hyperplane, right? So now in case of perceptron, all things which are positive will classify as class 1. All things which will fall below the hyperplane will classify as class 2, right? So this is the equation of a hyperplane, which is nothing but x1 plus x2 equals to 3, right? Now some of you, your friend comes in, no, I will not write this equation as x1 plus x2 equals to 3. I will write 10x plus 10x2 equals to 30, right? So he writes this equation as 10x1 plus 10x2, 10x2 minus 30. Will my classification error will get changed? Here it is 0, right? I am perfectly classifying my thing, so error is 0. If I multiply it with some constant c, you are saying that error will change, right?
Yes, sir. Sir, the data points are not changing, right? They're remaining same, right?
Yes, they are remaining same.
Then it will change, sir.
Everybody agree with this? Yes or no? If anybody in a class, somebody to disagree with this, they can unmute themselves and then they can come into a picture. Anybody in the class who just don't agree with this point? You need to answer. Say yes or no. If you are agree, say yes. If you don't agree, say no. Come on, type it. Okay, very good. So you all of agree with this point. Very nice. Very nice. So this is a wrong answer given by Rutvik. Things will not change, right? So things will not change. They just scaled it. I told you the distance, if my vector W is unit vector, right? So you will get an absolute distance, perpendicular distance from a hyperplane. If your W is not scaled, if your W is not unit, you scaled it, this distance d will get scaled in the same ratio where you are scaling your w. So if you are scaling your w with 10, then this absolute distance d will also get scaled by 10, but it will remain positive, right? If you scale your w with 100, then your distance will also scale by 100, but it will remain positive. Similarly, the point which are falling below the hyperplane, they were negative at first. And let's say the distance was d2. At first, when my unit vector was w, it was d2. You multiply unit w with 10 now, it is 10 d2. And it is negative now. It is scaled in the same ratio. And your perceptron algorithm, what it says, if it is positive, if it is positive, right? If it is positive, you say that it belongs to class 1, and if it is negative, it belongs to class 2, right? Can you see this, what I'm trying to tell here? Yes or no? Ritvik, do you understand this?
Slight confusion, sir.
What is that?
The suppose you've drawn the two x's here, will they remain at the same side of the line even after scaling it to a high value?
Yes, this is the equation of a hyperplane, right? This is what I have told you in 3 classes back. I told you just understand hyperplane very well. So I am just scaling the absolute distance now when I multiply my unit vector w with some distance thing, right? So this is what I have said. So now things will not change the side because equation has not changed. Can you see the equation which is x1 plus x2 equals to 3 is still the same equation, 10x1 plus 10x2 equals to 30.
Yes.
Right? So if equation is same, my hyperplane will not move an inch from there. If my hyperplane will not move an inch from there, then it means the points which were above and below were same there only. The only thing that will change is your perspective. At first you're seeing the distance absolutely, now you're seeing the distance relatively. It is a scaled version. That's the only difference.
Got it.
So here
Yeah.
we are multiplying it by scalar, right?
Sorry?
In this, we are multiplying our hyperplane with a scalar, right?
Right. Constant is a scalar.
Yeah. So, like, is it necessary for it to be positive?
Scalar.
Yes, sir.
So yeah, if I just want to multiply it with, I'm doing some absolute distance, so I'm multiplying it with vector w, so it will be that same. So if you are changing it, if you are multiplying it with negative, so things will be difficult. I don't want to bring that into here, but it is like this. So this was your w vector. So all things, this region will be positive, right? And this region will be negative. You understand this, Vedant? If this is
Yes,
your,
sir.
when you multiply it with negative 1, your w will get changed. So this is positive now and this is negative. So I don't want to confuse you guys there. So I don't want to take that vector. I don't want to flip the vector.
Okay,
So
sir.
better not to do, but it can be explained well. So I hope you understood your question, the answer that I have given to you. If the
Yes,
moment you write with negative, it flip the vector and regions will get flipped. So C1 will get C2 and C2 get C1. So not to do that, I want to stick to my constant should be non-negative. It should be greater than 0, right?
yes, yes, sir.
But you agree with that the points which were there before will be there afterwards also. Only the perspective this distance will be changed,
Yes, sir.
right? So this is the only thing. So now if I say that w will not multiplying w will not change anything, but it is just a relative distance, it means you can scale your w such that you divide this equation by eta, right? You divide this equation by eta, right hand side. So what will happen? Your new w will be w by eta, and your direction will be what? Phi tn, right? This is your direction. So it means you can always find out, you can always scale your eta to 1 and nothing will happen, nothing will change and things will be remaining same. So this is what we can set n equals to 1 without loss of generality. This is not what I mean to say. Now, if I do that, then you can always see this perceptron algorithm very classic, in a very classical way. I am just updating only when I am misclassifying, right? When I misclassify my Tn, right? So, oops, I think I have just changed it. This is phi. This is a typo. I will correct it. So this is phi. So if my sample was my sample was positive and it is misclassified, then I need to add my x to my w vector, right? If my negative sample was misclassified, then I need to subtract it from the w vector, because Tn is nothing but it's a 1 here, right? It is just a 1, and I am updating my w only when I'm misclassifying it. So if I am misclassifying for my positive sample, I should add it. If I am misclassifying for my negative sample, I should subtract it. So I'm subtracting that sample itself from w, right? Because you can just see Tn is either Tn is +1 or negative or -1. So if I'm misclassifying for my positive sample, I am adding my x to w. If I'm misclassifying for my negative sample, I am subtracting my x from w, right? Geometrically, if you see here, let's say this was your w vector, this black one, and you are misclassifying for your positive sample, red one. So this is your misclassification, right? So what you will do, because you have classified for your positive sample, you take this vector x, you add with this w vector, and the resultant vector will be this one, right? This is your new w. So it means this is your new w. It means it will change your orientation. So your orientation will be changed like this, right? Because w is always orthogonal to the hyperplane. You understand this figure? Can you quickly type yes or no? Very good. Very nice. Second one, again, if you misclassify it for the positive sample, this was your w, updated w. You take your vector, you shift it into a space, it will come here. Then the resultant will be this one, right? The resultant, oops, I changed the ink. The resultant will be this vector, right? Which is nothing but this. So it will just slightly change your orientation, right? And if it is negative, you subtract it. And you keep on doing it. So you just take a sample. If it is misclassification, you subtract or add it accordingly. If it is classifying accurately, don't do anything. You iterate over your data set once, twice, thrice, randomly. And finally, if you will converge. You will converge to a point where C1 is on one side and all samples belong to C1 is on one side and the rest will be on the other side. And it will happen only when your data is linearly separable. If your data is not linearly separable, your perceptron algorithm will run forever and it will never halt, because it will always find an error, because your hyperplane is not good enough to separate the space such that the data should be fall apart with 100% accuracy, right?
Sir,
Yeah.
if suppose for the algorithm it would take five iteration of the algorithm to get a plane that is perfectly classifying it. If suppose I were to not know it and I were to run the algorithm for 10 times or more, would I still be able to get at least correct hyperplane for it?
No, once you get after 5 iterations, you find a hyperplane, it will not move, right? Because you are only moving when you are misclassifying it. The moment you just do it after 5 iterations, you are classifying everything perfectly.
Oh,
so
right.
updation will not do. You don't do updations because you are doing updations only for misclassifications, right?
Right.
Okay. Any other question? So I hope you understood this perceptron algorithm. This is what it is. This slide is showing that your contribution to the error for misclassifying pattern will be reduced. So the operations that you are doing here will always or minimize the error. How it is doing, what it is shown here. So this is your updated W, right? The updated W can be written how? What way? It is like old W plus phi Tn, right? Phi T. This is what your uh, equation of new W plus old W. So tau here is just like the time. So this is your old W. You keep this old W here in the equation. So it is saying new W, this is your new W transpose phi and Tn, right? Phi and Tn. So you have just replaced this W here. Now you multiply it. So then you multiply it and you get a negative. This negative is already here, right? So this is first term you got, right? This is the first term you got, and this is the second term you got. You see this second term is nothing but it is a transpose of each other, which is, you can write it is the square of a norm, and square of a norm is always non-negative, right? Because you take a, you can prove it, right? Because square of a norm, every term is positive because every term is a square. So if you take negative number, the square will be positive. So it is a non-negative number. You subtract it, you will get, so you will subtract it, you will get less negative number, which is greater, right? So that's how you are saying that after each updations, you are minimizing your error. But it is, you are minimizing it for that respective point. It may be possible for that respective point you are minimizing error, but the moment you change your hyperplane, it now misclassifying further points, right? For an example, this was a case. So you were trying to update the hyperplane such that it will be accurate like this, but the moment you will do, you will misclassify for this point. So it will happen. You will do it again and again and again, and if it is linearly separable, it will converge, right? So the limitation says there are infinite solutions for a linearly separable data set, and it depends upon what is your initialization of W. For linearly separable, non-linear separable algorithms, it will never converge. You will never get to know whether it is that your data set is linearly separable or not. If you don't know that, you cannot trust this algorithm. You don't know like whether it is still searching or because your data is non-linearly separable, that's why it cannot find a solution. So it doesn't provide you probabilistic outputs, and it doesn't generalize. It is just for two classes. Right. Fine. So this is all. I just missed one slide in between. That is now the title of this lecture is Probabilistic Generative Models. So in probabilistic generative models, so far I have been discussing discriminant functions. In discriminant functions, you were about to give the motive of discriminant function is if you feed an x to it, it means unknown sample, it will directly give you a class. How you were doing for linear discriminant models, you were trying to find out a hyperplane. If it is on the one side, it doesn't matter. You don't care about the probability. You just spit out that if it is above the hyperplane, it is class C1. If it is lower, it is class C2. So that is what discriminant functions there were doing. So you were directly giving the class labels. But we are more interested in finding out the posterior probabilities, and based on once we calculate the posterior probability, we will decide then whether we should reject it. Is it okay to give a class label, or we should reject it? We have discussed all this in the previous class. So now the motive is not to give directly a class label, but we should find out the posterior probability. It means for a given x, what do you think it should belongs to class 1, right? It should give you a probability. And if probability C1 is greater than C2, then you say that this x belongs to a C1, else it belongs to C2. But discriminant functions, they don't do this for you. They were doing everything on their own, and they were directly giving you C1. So here in this approach, first you are inferring it and then you are deciding it, right? So inferring plus decision, right? This is what you have to do here. So now the ultimate aim is to find out the posterior probability. There are two ways to find out the posterior probability. One is with generative models, another is with discriminative models. So here I am discussing generative models first. Then I shall be discussing discriminative model. So right here from this slide onwards, I will be discussing probabilistic generative models to infer the posterior probability for a given sample, right? Any question on this for clarification? You need to well understood the motive of the lecture. So here I am trying to infer the posterior probability. There are two ways to infer the posterior probability. One is with generative models, other is with discriminative models. I am here mentioning the generative models, right? Why we are saying them generative? So generative, we are just trying to model it with these probability, prior probability, right? This is my prior probability. This is my conditional probability, and this is the evidence probability, right? Can anybody tell me how the other way I can rate the denominator? Anybody in the class? Can anybody tell me how I can write the denominator? So this is one way I am writing it. What exactly it is telling? What probability is exactly telling you? It is a probability of what?
Probability of X.
Very good. It's a probability of X, right? You are seeing how I see it, right? I just want to share my view, how I see it. So this is how I see it. This is a probability of seeing class C2. So let's say there are two classes, C1 and C2. So this is C2 class and this is C1 class. So this is a conditional probability, but seeing C1 and C2 itself is a probability. So let's say if I toss a coin, that it comes with 60% probability for C2, with 60% probability or 0.6 probability, and 0.4 probability it belongs to C1, right? So first I need to choose whether I need to go for C1 or C2. So I toss the coin, and if the coin comes for head, I will say it is C2. If it comes for tail, it is C1, right? So choosing class itself is a probability distribution. Once I choose a class, then I need to find it out. What is the probability of choosing a X from that class, right? So for an example, if this is my X, so I choose class C2 with 60% probability. So then what do you think? What is the probability of seeing X from C2? Anybody? What is the probability as per this diagram? What is the probability of seeing X from class C2? Zero. Very nice. Very nice. Because almost zero because there is a very less chance. So you are just find out now this is a probability for class C1 for C2. Then you just go for class C1. Then the probability of class C1 is 40%. What is the probability of seeing the same X from C1 now? So it is quite high, right? So you are seeing your X in every possible way. Either it can be generated from C2 or it can be generated from C1. You don't care it. So you are marginalizing it. You don't care it whether it is coming from C1 or C2. The ultimate aim, you just want to see the X. So it means you are only want to see the X. Right? But there are ways to get the X. Either you get from C2, right? This is a term, or either you get from C1. This is the first, this is the term. And if there are K classes, so for every class, you find it out what is the prior probability of seeing that class. And if you see that class, what is the probabilities of seeing the X from that class, right? So if there are K classes, you do this exercise K times and you sum them up. It means it is the probability of seeing the X. It doesn't make you are not caring whether it is come from C2, C1, C4, Ck, right? You're just interested in seeing X itself. So it is a marginalized probability, right? And what this numerator says, You are normalizing it. You are normalizing it with this probability. This is a total probability of seeing X. And what is the probability of seeing it through C1? Right? So you see that from C1 it is almost 0. So the total probability for seeing X from C1 is almost 0. And for C2 it is almost 1. Because a major portion of X is generated from C1 itself. So you are normalizing it. It will always normalize sum to 1. Right? So this is generate in a sense you can generate your data set. If I give you all probability of C1, probability of seeing C2, conditional probabilities of seeing X from C2 and X from C1. So you can generate your data set. So if you can generate your data set, you can always that's why it falls into a category of probabilistic generative models. Do you agree with me? You can generate 100x from this this distribution. If I share this distribution to you, if I share PC1, if I share PC2, and I share these conditional probabilities of X from C1 and X from C2. If I share these 4 parameters to you, right, you can generate your 100 points, right, from this data set. Do you agree with me? Very good. Yes, you can do it. You just first toss a coin, see whether I want to go for class C1 or C2. Once you toss a coin, you just select one of the class, and then you find out the conditional probability of seeing that text, and you do it randomly 100 times. You just produce 100 samples, and it is nothing. You are creating a data set. So that's why they comes under the generative models. Okay, this is one thing. So once with equipped all this knowledge, now I want to proceed further. So here we are doing some mathematical juggling. We are bringing this numerator to the denominator in this way, right? In this way, numerator will cancel denominator. So I will get this one here. And I will get this fraction, probability of C1 upon probability of C2 something. Then I take a exponent and log. Exponent will cancel the log, so it will not affect anything. Then I take the negative of this and flip this fraction. So now I get probability of C1 on the above, right? So I will flip this thing. So probability of C1 come in the numerator and probability of C2 will come into denominator. So effectively, and I am representing it with A. So effectively, this will not change anything. I have just juggling with these terms, and this is all mathematics. So effectively, I have not changed anything, but representing this way, what I am seeing that it is nothing. I can write my posterior probability in terms of sigmoid function, right? Where my parameter A is nothing but can be shown this way. It is the log ratio of these. Sometimes this is known as a base factor also, right? So this is the ratio of log ratio of this probability of C1 upon probability of C2 multiplied by the conditional, like class probabilities, right? So it is simple, nothing intuitive here. We are just doing, so we are bringing numerator term into a denominator and then writing it in this way. I hope this is not confusing you. Is it clear to you guys? Yes or no?
Yes, sir.
Right. So it's some Yashdeep is saying, can we say likelihood equals to, no, we can't say this likelihood. It is not likelihood. Why you are cancelling C1 and C2? You can't cancel this. Right? They are different probability. So just take it this way only.
Sir, is probability of C2 is equal to 1 minus probability of C1?
Right, exactly. Yes, it is there. If both are 0.5, then you can cancel it. Otherwise, it is they are nothing but it is just a complement in a space of 1. Right. Okay. So this is my class conditional probabilities. This is my class conditional probabilities for two different classes. Let's say this is for C1 and this is for C2. And once you rewrite it into a posterior probability, right? So this is a posterior probability of seeing C1 for a given X, right? And assume that your posterior prior probabilities are same, PC1 equals to PC2. Then you will see this kind of a output. Here, this is a space where they are dividing somewhere, right? So till this space, you will get on probability of C1, and here you see that it is more blue. So probability of C1 is almost 0. If it is almost 0, so you are left with probability 1 minus PC1, it is PC2. So that's why here though this graph is for probability C1 only, but it is like a colored graph. So red is like 1 and blue is like 0. So here the probability of seeing C1 is 0 almost, right? So that's why, so this is a class conditional probability. And if you see the posterior probability, assuming that your prior probabilities are same, so you will get this kind of posterior probability here, which is represented in terms of sigmoid function, right? Okay. So multi-class classification, what I do redo the same thing again. So I have numerator, as I said in my explanation, that you can see if there are 3 classes, C1, C2, C3, and you want to know like what is the probability of seeing this X. What you should do, you see what is the probability of seeing this class 1, C1, and then from C1, what is the probability of seeing this X. This is one term, right? This is one term. Then you say what is the probability of seeing C2, and from C2 what is the probability of generating this X. This is the second term, right? This is J equals to 2 now. And then you take the third term, what is this probability of seeing class C3, and what is the probability of seeing X from that C3. This is the third term, right? Now J equals to 3. So if there are K terms, so you see what is the probability of seeing CK class, and what is the probability of seeing X from that CK class. This is the K term. You add them up. It is nothing but seeing the probability of X. It is a normalizer constant here. It is in a denominator. And in numerator, you are seeing just only one class. So what is the probability of seeing C3, right? What is the probability of seeing C3, and what is the probability of seeing X from that C3? So you are now taking only one component and putting that one component in a numerator and normalizing it with the total probability of seeing X, right? This is how you're doing it. Now what you do, you just take a log of every term and take exponent so that they cancel each other. So you can rewrite this thing in this way. So here you have taken every term. This is your term. You take a log of it and then take exponent of it. Then take exponent of it. You can rewrite this thing now in this way, which is nothing but it is a normalized exponential terms, which is also known as softmax function, right? You see this term frequently in deep learning or in neural networks. So we are normalizing things here, so they will have a probabilistic view, right? So, and they will add up to and why it is known as softmax, because if one term dominates, let's say if one term is 0.8 and the rest 2 terms is 0.1 and 0.1. So if you take the exponential, say, softmax function over it, it will give you 1, 0, and 0. So it will highlight that term specifically which is highest in distribution. So it is nothing but taking a maximum out. So that's why it is known as softmax. So it is not max, it is a softmax. You can take a derivative with respect. So this function is not like this way. You will not find a king. So it is softly taking this thing, right? So it is a softmax function. The rest things will remain same, right? Okay. So till here, you have any questions? So we are discussing probabilistic generative models. There are two cases: binary classification, multi-class classification. For binary classification, we found out that this can be represented in sigmoid, and for binary classification or multi-class classification, it can be represented as an express softmax function. Right? Any questions so far?
Sir, for the softmax, the values have to be greatly differing.
You don't have any control over it, right?
Okay.
So you will be taking W, and these W will be spitting out some probability. Then you are normalizing it, and if it is U, then you will take a derivative and then tuning it.
Right.
The guys who are understanding it, they should understand it by heart, that we are actually formulating a error function which can be differentiable, and we always take it, because variable is a parameter, we'll always differentiate it with respect to the parameters, and we tune our parameters, right? So W can be start from anywhere, and gradually the idea is to find out that W which will agree with our data set. What is my data set? That is given to me in my pen drive, and if it is having all dogs with 1 and all cats with 0, it should agree with me, the W, with the data set. So this is the crux of machine learning. You are actually framing a error function, and then you will how you're framing an error function. You are comparing your predictions with the true values in your data set, and then whatever the difference will be, you just take a derivative, because the difference, if it is differentiable, because you're taking a square, let's say in very simple sense, then you take a derivative and you try to tune it into the direction where the difference can be minimized. Right? This is how you do it. Sometimes you will get an analytical solution, sometimes you don't. Analytical solutions means that you will, in one shot, you will get the value of W, like in Bayesian linear regression. Or sometimes we need to take slowly one by one steps, like we have done in Perceptron. We don't have analytical solutions there, right? So for every sample, we take one step, and if it is wrong. So this is what we have done. In next class, just to frame the idea tomorrow, in next class, I will tell you how to find out the parameters. How to find out the parameters. It means just see very clearly here. This is all what we have seen, right? This is all what we have seen. But still, I don't know what is the probability of class C1, what is the probability of class C2. Right? I don't know this thing. I don't know this thing. I don't know this thing. But there are so many unknown things with me. So if somebody gives me a data set, right? Somebody gives me a data set like this, and he wants to find out some hyperplane which will agree with this thing. So there, I am for trying to find out some hyperplane W, right? How to do that? This is all fine here. So we need to assume some conditional distributions here. Like we need to assume, just to agree with this structure, I say that this class is Gaussianly distributed and this class is also Gaussianly distributed. This is my assumption, right? The moment I take this assumption, it means, how can I show my class C1? Can anybody tell me? How can I show my class 1, C1? The moment I say it is the Gaussian distribution over C1 and C2, what are the things that I need to represent C1 now?
A mean and variance.
Mean and variance. Very nice. And for class C2?
Same thing.
Same thing. Mean and variance. So for prior probabilities, I am interested in knowing what is the prior probability of seeing, what is my mean and variance, right? What is mean and my variance? The moment I know my mean and variance, then I can able to find out what is the probability of this X, what is the probability of this X, what is the probability of this X, right? So I can able to find out my conditional probabilities the moment you give me the mean and variance. And the prior probabilities, how I will get? It is nothing but it is a ratio in my data set. What is the frequency I can see C1 in my data set? What is the frequency I can see C2? So if there are 8 samples out of 10 that belongs to C1, it means I have 80% probability of seeing C1. So my prior probability is 0.8, right? So class conditional probabilities, I am framing it with a Gaussian distribution. Class conditional probabilities, I am framing it with a Gaussian distribution. So I am interested in framing out, knowing out what is my mean and variance. And tomorrow I will do this exercise for you. We'll restart it again. You frame your questions in your head to start with. And then we will find it out how to find out these mean and variances, right? And how to find out the prior probability, PC1 and PC2. So now the things left to us with some assumption. I started with the assumption when class conditional probabilities are PC Gaussian, and then with the assumption that my class conditional probabilities is Gaussian, then I will try to find out the parameters, which is nothing but mean for class 1, mean for class 2, variance for class 1, variance for class 2, and what is the ratio of C1 and C2? What is the prior probability of PC1, PC2? Is this question construct clear to you? What we will go into tomorrow?
Yes, sir.
Anybody, can you write yes for if you understood this thing? Because it is very, very important to understand the question itself. Fine, very nice. So, okay, then we'll start tomorrow. Thank you very much.